Okay, so today we are going to learn about recursion. So all of you please observe the figure what is posted here and try to understand what would be recursion. Can anyone convey your observation? Please observe the diagram, observe the figure given here. What's your understanding from this diagram? I hope I am clearly audible. Can I get some response, please? Okay, so recursion. So recursion is a method of solving bigger problem by solving smaller instances of the same problem. So a function can solve any sort of problem so by calling itself. Okay, this is very, very important key terminology here. A recursion is a process where a function or the process can call itself. Okay, so again and again it can call itself, and then until it gets a condition of solving the problem. That means until it gets the solution for the problem. So it is important to impose the termination condition of the recursion. So until and unless you are giving that termination condition or the end part, then you are not able to stop the process. It will keep on continue. So that is what the idea behind the recursion. So recursion is a method of solving a bigger problem by solving smaller instance of the same problem. So here the recursive function will call itself. There may be multiple recursive calls for to solve a single problem. Okay, so you can observe the same concept from this image also. You can observe from this image also. You please, all of you, please go through the lines given in that image, statements given in that image. I hope you are all able to get an idea. So we are trying to fix a problem. The problem created while we are trying to fix a problem. Okay, so likewise a function it call itself. Okay, problem is created while we are trying to fix a problem. Similarly, the problem is created when we are trying to fix a problem. So likewise the process will keep on going. So until and unless if you give some pause or if you give some termination condition, it will not be ended. Okay, so this is what the basic idea behind recursion, but it is very much beneficial. Okay, in what way it is beneficial and all we will be seeing in the upcoming slides. Okay, so I hope all of you might clear about what is recursion. This image as well as the next image must convey you a clear picture of what is recursion. Okay, so, then let us look into this example. So you are supposed to find a factorial of 5. Okay, so how we will be calculating the factorial? The factorial of the 5 can be calculated by 5 into 4 into 3 into 2 into 1, right? So the same thing that we are supposed to convey the information to the system or to the computer in the form of what coding. Okay, so here we are writing the pseudocode of the form as such, return 5. That means 5 into 4 factorial. Again 4 into 3 factorial. Again 3 into 2 factorial. Then 2 into 1 factorial. Then 1 into 0 factorial. That we all know very well that obviously we can compute the 5 factorial by repeatedly calculating the factorial of 4, 3, 2, 1. But each and every operation performs the same concept or involves the same concept of calculating the factorial. Okay, then we can collect the result right from the bottom as 1 into 2 as 2, 2 into 3 as get 6, and 6 into 4 causes gives you 24, and 24 into 5 gives you 120. Okay, so this is what the basic idea behind the recursion process for calculating the 5 factorial. Okay, so in a simple manner it is given here. We are all able to understand it clearly, I think. Okay, so next one, example 2. Here we are going to see how we are able to implement the recursion for calculating the exponent value. That means 2 power 3 is an exponent. How we are able to calculate, how we are able to convey this information to the computer is with the help of some functions. Okay, so here that function is defined as power. Okay, so the power of 2 comma 3 can be recursively defined as x power n equal to x power n minus 1 star x. Okay, so this can be translated as into a recursive call as power of x comma n minus 1 star x as such. Okay, you are able to understand, I think. So once again, you please go the statement, that is recursive definition, as well as the translating recursive call, how it would be, how we are able to convey the information to the computer in terms of recursive call. Okay, then we can define the function as def power of x comma n. If the n, or if the what's that exponent value is 0, obviously you will be returning the value 1. Otherwise you are supposed to compute the power value until it gets 0. Okay, so x power n can be calculated by, in a recursive way, by power of x comma n minus 1 into x. Okay, so this is what the basic, very fundamental methodology to calculate the exponent value of a number with the help of recursive call. Okay, so you can look into this calculation part. So initially that we are having 2 power 3, no, so that 2 comma 3 will be passed as an argument to the function. Here 2 represents the x and 3 represents the n. Okay, then while we are calculating that power, what would be the formula? Power of x comma n minus 1. So x is written as it is as 2, and n minus 1 is 3 minus 1 equal to 2 into x. Okay, so likewise the sequence goes till the value of n minus 1 is 0. So once it gets 0, that is what the stopping case. Then you are able to compute the total value of that power. Okay, so of that exponent computation. Okay, so now it is 8. Okay, I hope all of you are able to understand the function of recursive call in calculating the power of two numbers. Okay, so the exponent can be represented in the form of computer understanding code, such as power of x comma n minus 1 into x. Okay, so this is what the another one simple example. Then we will get into the part of computation as such. You are all able to understand from this diagram. Look into this bottom up part here, x equal to 2 and n equal to 3 initially. Then you are computing the next step as whereas n will be reduced to n minus 1. So that here it is n 3 minus 1 is getting 2. In the next step it is getting 2 minus 1 is getting 1 and 1 minus 1 is 0. Then finally it will, since it is 0, then it will return 1. Then from this computation you are able to collect the values as 1, 2, 4 and finally you are able to get the result as 8. Okay, now you are all able to understand the concept of how the recursive call helps you to compute the value of the exponent as 8. Okay, so please go through this diagram. If any doubt in this, you can call me. You can ask me, please. We are computing the power of x comma n. That is, we are, in order to compute the exponent value, how the recursive function call plays a vital role. How it can help you to arrive with the result of 8. Okay, that is what depicted in this slide. You all please go through it. Okay, then we will move to the next one. Example 3, towers of Hanoi. So I hope all of you might hear about this problem. This is a very good example for the process of recursion. Okay, so let us get into the problem. This is the problem statement. So mainly you are supposed to transfer the blocks from one pole to the another pole, that is from source to destination pole. You are supposed to move the rings here. So objective of this puzzle is to move all the rings from source tower to the destination tower. Okay, so here in the source we are having different rings. They are stacked together, one over the other. matter. Okay, so here we have some sort of rules to be followed. So this kind of arrangement is not a correct one. This is a disturbed way of arranging the rings. So we are supposed to follow the rules of arrangement, such as only one disk can be moved at a time, and only the top disk of one stack can be transferred to the top disk of another stack. The third rule is larger disks cannot be stacked over the smaller ones. Okay, so I hope you are all able to understand this rules. Okay, the only one thing, the thing is only one disk can be moved at a time, and one more thing is the smallest disk cannot be kept at the bottom. Okay, so it should be in a proper weight management. Okay, that means what, the larger disk should be at the bottom, over that the next level one, and over the medium size disk, over that you must have the smaller one. So likewise the disk arrangement should be as such. Okay, so please remember these 3 points. Now we are going to do this process of arrangement of transferring the disks from source to destination. Can you all think about the solution, how we are able to do it, how based on the criteria we are supposed to achieve the result? So any idea? Can I get some idea from this? So here we are able to compute this, able to achieve the result in 15 steps. Okay, so those number of steps as well as the tricks vary person to person. In your own perception, you all can solve the problem, and you can play. I will share the link also. You can play based on your own interest and also your own idea. Okay, in that particular link, it is an animated link game part. You are able to do the process of this disk arrangement. Okay, so in my perception, whatever I have taken here, you can consider as a sample result. Okay, sorry, sample solution. Okay, so move one, initially the disk, the topmost disk is moved to the helper tower. Okay, then in the move 2, the next level of disk move to the destination tower. You are all able to understand, I believe. And in the move 3, you are all able to see the difference. Now the disk in the helper tower is moved to the destination tower, and in the move 5 and 4 involves that the smallest disk in the destination tower is again moved back to the source tower. Okay, so that now what's that, now destination tower having only one tower as well as the helper tower. Then move 6 involves that the completely you are transferring the what's that, a block ring from the destination to helper tower. Okay, so now once again what you are able to do in the move 7, you are able to move the topmost disk of the source tower into the helper tower. Okay, so next, in the next step, our goal is we are supposed to move the disk to the destination. So now in the source star we are having the bottommost block, so that we are able to easily move to this particular ring to the destination. Then once again we need to try to stack the disk in the order of its size. Okay, so once again the process starts from the helper tower to other movement from the source to destination. Okay, you can view here as move what's that, topmost tower disk to destination, and in move 10 and 11 says that what, you are moving from the green color disk, no, so that is moved from helper tower to source tower. Then the smallest disk is moved from the destination to the source. Okay, so likewise the swapping process keep on going. Okay, so this swapping process makes you to do the arrangements in a proper order as per the rule. So how this movement is happening, what is the relevance between the recursion and also this particular arrangement is, here we are swapping the disk from here and there and there and here likewise, based on the availability of the pole or the tower and its freeness, and also the size of the disk what we are moving from one tower to another tower. So here we are supposed to determine which movement will give you a feasible solution of arranging or stacking the disk in a proper order. Okay, so in this move 15 you are all able to see the completed arrangement of the, or completed movement of the disk from source to its corresponding destination. So likewise you are all able to do the process repeated. You are doing the repeated process. So such kind of repeated process can be effectively handled with the concept of recursion. Okay, so I hope you are all able to understand, right? So for in terms of recursion, we have seen three examples so far. Okay, one is factorial problem, another one is calculating the exponent of a number, the third one is what's that, tower of Hanai problem. Okay, yes, a fourth example, I will share the link in a chat box. You can play the game, okay, in the end of the session. Okay, so here we are having the furthermore representation related to the tower of Hanai problem. So you can go through the slides, I will share it. Okay, so here we are having totally 4 disks from pole A to in pole A we are supposed to move that to the destination pole C. Okay, so this is the same way of our previous slides, how the transaction was happened from one pole to another pole, how the middle pole is supposed to supposed to move do the changes and all. So all those things already we have seen. So this is another kind representation for the same problem. Okay, then let us come to this problem, come to this end. So here I, before that I let you know, 1 minute. So here you are all able to see the states. So initial state is where the pole A consists of all the 4 rings. Okay, then we move n minus 1 disk from A to C. So our destination pole is what? Destination pole is C. Okay, so move n minus 1 disks from A to C in the sense. So we are all, anyway we are all supposed to move all the disks from source to destination. So that movement each and every time you will be representing that particular disk in terms of n minus 1 disks from A to C, like that. Okay, we will see in the coding part also. Then third one, move 1 disk from A to B. So in the previous slide we are all able to see that there is only 1 disk from A to B, so that in A, so it can be moved to the pole B. Okay, then further rest of the disk from C can be moved to B. Okay, so in a sorted way it is given here, but it is not possible to move more than 1 disks at a time. You are all supposed to do various swaps from here and there, then only you are able to achieve the result as shown in figure B. Okay, so that is as shown in the pole B. Okay, so how the pseudo code will be, how you are able to represent this swapping process to the system. Okay, so for that you can define the function in any name, you can define it. Here n represents the, what's that, n represents the total number of disks in the process, and source is the source pole, and destination represents the destination pole, and spare represents the what, it is a mediator pole where you can use it for intermediate swapping process. Okay, so you are supposed to move the disk from source to destination. So that swapping process involves the recursive call of the same function, tower of Hanai. Initially it is n. So once you have started swapping it, then you will be moving to the topmost disk to the rest of the pole, whatever it may be a destination pole or it may be a spare pole. Okay, so according to your interest and movement, the destination, source, spare and destination will be swapped together. Okay, so the thing is, that's why it is highlighted in three different colors. Okay, so either each and everyone have their own methodology of solving this problem. So accordingly the code can be written, and the basic thing is you are supposed to swap the position of the tower here. Okay, so that you are able to push the disk into the respective tower based on the function call what you have initiated here. So here you are all able to understand the difference. So while I am initiating, I am calling the function, I am defining the function with a number of disks, source, destination and also the spare. Okay, then while I'm initiating the swapping process, the tower also getting swapped, because we are not following the same sequence for all the disks, no. So we are all supposed to move here and there, so that it is denoted in a different manner. You are all able to understand the process of swapping here. Okay, so you can try this tree, okay, recursive tree. You can try with your own solution how the recursive tree can be structured. Okay, so based on your solution, you just work out in the paper how you are able to swap the disk from pole A to pole C. Then based on your methodology, you try to derive this tree. Okay, this tree is for the previous solution. Okay, then the thing is how the process is happening, how the swapping process is happening, what would be the differences while how the disks getting reduced. We are calling the method, sorry, we are recursively calling the function with the disk number as n minus 1, right? So that that count of the disk will be keep on increasing, keep on reducing, and based on the pole which you have opted for choosing, accordingly that swapping process will happening here. Okay, so these are the representation of this swapping. Okay, you are all able to understand while you are solving the problem by your own. So how this count is getting reduced, how it is coming to the count as from 3 to 1. Okay, simply it is a reduction of the disk from while you are moving from one pole to another pole, obviously the count get reduced. Okay, so likewise you please go through these things, you are all able to clearly understand the concept what we have discussed so far. Okay, so it is a step by step coding representation, pseudo code representation of these things. So just it is a calculation, you can do it. Okay, then how we are able to understand the, or you are able to calculate total number of moves in a problem. Okay, for example, if you are having 4 disks. Okay, if you are having 4 disks in your tower of Hanoi problem, then how many number of moves you are supposed to do can be calculated with the formula that moves of n equal to 2 into moves of n minus 1 plus 1. So if there are 4 disks, you are able to solve that problem. If there are 4 disks, then you are all able to solve that problem by 2 power 4 minus 1. Then you are able to solve it by 15 different moves. Okay, so this is what the formula for calculating the, what's that, the number of moves before initiating any problem. You can do the calculation and then you can start doing the problem. Okay, so this is what the formula you are all supposed to know. Okay, then one more example for this recursive process is Fibonacci series. So you are all know very well, I hope. Yes.
Ma'am, I have a doubt. Like we have a stack, and can we like make another stack, and it will be in reverse order.
Okay.
Then we will arrange it into a new stack that will be in the correct order, so that it will change from source to destination with not much number of moves. It will be just twice the moves.
But that cannot solve all the 4 disks movement, no. So if we can
No,
define
ma'am. Like it will be like first you showed a photo about like the disc with the colors, right, in triangle,
yes, yes,
triangular.
yes, yes, yes,
But the triangle will be in the reversed order. Like it will be upside down in the second one,
yes, yes, yes,
and on
yes.
the third one it will be on the right way.
Okay, so actually that is not a right one. That is actually it should not be as such. That is what I denoted in that slide. This is what you are coming to say, right? Oh, 1 minute, I will show. This is what you are coming to say, right?
No, ma'am. But the inverted triangle will be in the helper tower, and then we'll stack it again so that the number of moves will be twice only.
Okay, 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 okay. So you are saying that inverted
So less
triangle,
number
but
of moves.
inverted
Yeah.
triangle, as per the rule, if you want to proceed as such, that inverted triangle cannot be happens. No,
Why, ma'am? I don't know.
no, I'm telling you. So as
Uh,
per the rule, if one disk can be moved at a time, that is one thing, and that is you know very well. The thing is, disks cannot be stacked over the smaller ones. So if you are trying to stacking with the smaller ones, bigger one over the smaller one only, you are able to get that triangle, inverted triangle form. No.
yes, ma'am. Yes.
So that is, as per the rule, it is not possible, right?
Yeah.
So that based on the rule only we are supposed to move. So if there is no restriction among in terms of its arrangement and its size, in the sense you can simply cut down the process with the 2 steps. Okay, that is okay, very good idea. But there is a limitation. There is a rule that we should not stack the bigger disk over the smaller one. So we are obviously we need to move accordingly. Are you clear about your doubt now?
Yes, ma'am. Thank you.
Okay, thank you, thank you. Okay, so let us get into this Fibonacci sequence. So all of you know very well, I think. So Fibonacci sequence comes with 0, 1, then again 0 plus 1 gives you 1, then 1 plus 1 gives you 2, then 2 plus 1 gives you 3, 3 plus 2 gives you 5. So likewise, we are repeatedly adding the current value as well as the previous value. So that here also the recursive process takes a vital role. Okay, so you are all able to see this pictorial representation also. By this, you are able to understand what is happening in the Fibonacci series. Okay, so let us get into the pseudocode part. So here I am initiating a function, defining a function fib with the number n. This represents that it is a limitation. Okay, then so I am keep on calculating the sequence, until and I reach the limit. Okay, so here in this tree you are all able to see the sequence as function analysis for Fibonacci of value is given as 5. Okay, so how you are able to calculate Fibonacci of 5 is obviously it should be starts from the value 0. Obviously all kind of Fibonacci sequence starts from 0, and also one padded with that 0. So 0 and 1 are default values in the Fibonacci sequence. Then from that, how much you are supposed to explore will be given as a limit, such as n here. Okay, so here it is given as 5. Okay, so you can look in, you can traverse right from the bottom of the tree. So Fibonacci sequence, that means fib of 1 and fib of 0 obviously give you 1. Okay, again fib of 1 and fib of 0 will obviously give you 1. So 0, 1, 1 will comes. Next you are coming to the n value, it is getting reduced, n minus 1 plus n minus 2. So for example, if I'm having n as 5, then 5 minus 1 plus 5 minus 2 would be the value which I am going to compute for that particular step. Okay, so you're all able to understand, I think. So initially we all begin with 0 and also 1. Okay, so here the computation takes place up to the limit, that is if you have mentioned as 1, then 5, then it will go up to that. Okay, so fib of 2 and fib of 1, 2 plus 1 gives you 3. Then again what you are supposed to do, 3 and also its previous number, 3 plus 2. Okay, so sorry, 1 plus 1 give you as 2, and then you are able to get the fib sequence as 1 here. Then 2 plus 1 give you 3. Then up to this, up to the limit of n, or that is 5, we are supposed to proceed. So you please observe the tree. If there is any doubt, we can have a discussion over it. Any doubt on this very simple concept only? So I hope all of you might understand this Fibonacci sequence. Then if any doubts, you please let me know. Then we will move to the next topic. Okay. So here we have discussed about the recursion and various applications, in the sense some examples related to recursion we have seen. One is what is that, factorial of the given number. Another one is exponent, calculating the exponent value. And the third one is Tower of Hanoi problem. Okay. Then what is the fourth one? Fibonacci sequence, calculating the Fibonacci series, how the recursive call or the recursive function plays a vital role in these examples and all we have clearly discussed. Okay, so these are the application of the. In our previous class and all, we have discussed about the application of the stack in solving the expressions, as well as the what's that evaluating the expressions. So that's all about the application of the stack. So next on the important topic is about the queues. Okay, so queue and all very much important data structure. Okay, so in terms of our queue representation, we can have it in two different manner. One is linear way, another another one is circular manner. Okay, so here queue data structure basically involves basically related with this particular figure. So you are all able to see the figure and can understand, I think. So we are waiting in the queue for entering into the what's that theater, for entering into the ration, or we are standing somewhere to collect some train ticket, like that. Okay, so here we are the person who is in the first position of the queue is the front position. The a person who is at the back of that queue is the rear position. So the position of the last person can be updated with the upcoming persons. Okay, but the position of the front, the person who is standing in the front, cannot be changed once until and unless he left from the queue. Okay, so this diagram tells you what idea about queue implementation. So in terms of our queue, we are having front end as well as the rear end. So front end is the place from where the person can be exempt from the queue or exit from the queue. Rear end is the position or is an end where a person can be added. Okay, so similarly, in the same concept, we will be depicting in our programmatical applications also. So here we will use the queue for representing the data elements in the form of first in first out order. So we have seen that, we studied that stack is of LIFO order, that means last in first out order, but queue here is the first in first out order. It is a first in first out format data structure. It is a collection where whose elements are added at one end. The elements added at one end, I already told you in this diagram, we are able to add one more person at this rear end. Okay, similarly, we can delete or remove a person from the front end. So that is what denoted here as we can add elements in the rear or a trail of the queue and removed from other end, that is the front or head of the queue. Okay, so rear and front are the two important key terminologies you are all supposed to remember. Okay, the next one, any waiting line is a queue. This is an example. Then we can check out line at a grocery store. If you are waiting to get some grocery items, then obviously we will be in the queue. Then cars at a stoplight, that means if we are waiting in some signal, means obviously there will be some queue over the cars, right? Then assembly line, we are moving to in the form of queue only. Okay, so likewise there are a lot of real-time examples for our queue implementation. So look at this diagram. So here we are having the elements as AA to EE. So the element which is at the front of the queue, at the first position of the queue, is denoted by the pointer called front. The element at the end of the queue, that is the last element, is pointed by the pointer called rear. Okay, so this is one more, this will give you much more clear idea about what is queue. So the person who entered as a first person will leave from the queue as a first person. Similarly, a person who entered as a last person obviously can leave left from the queue as a last one. Okay, so this is what the process. Okay, removing the element means we are obviously can remove the element from the front only. So if you want to add an element, we can add the element or the person at the rear end only. Okay, so now you all get into the application. That is what already we have seen. So one more examples, few more examples also here for any kind of problem involving FIFO data. So for a printer queue, so we are keep on giving some printing. So the a document which reaches the printer as a first one will be printed first. The rest of the documents will be printed according to their order. Similarly, keyboard input buffer, whatever the key you typed, that will be printed there as a first one. Similarly, guy event queue. Okay, so we are trying with many web applications. So how that guy events and all activated is in the form of queue only. Okay, then operations. So what are the operations we are all able to perform in the queue is we can do is full, enqueue, is empty, dequeue, and display. So is full means it determines whether the queue is full or not. Enqueue means add an element to the rear of the queue. Is empty, it determines whether the queue is empty or not. Dequeue means removing the element from the queue. Display means it prints the value of the queue. So likewise in stack, we are having operations like is full, enqueue, dequeue, is empty, and display. Okay, so elements of the queue involves array and also what of front end as well as the rear end. So front end from which we are able to delete the element, rear end where we are able to append or add the elements. How these operations happening and all will be seeing in the next slide. Okay, so look into this image. So here we are having front. So initially you please make note of it. When the queue is empty, very very important point, when the queue is empty, both the front pointer as well as the rear pointer will points -1. Okay, will be assigned as a value as -1. That means it points the location of as -1. So when there is an empty queue, obviously the both front and rear end will be denoted as denoted by -1. Then suppose when you are when you are inserting an element, obviously what's that, front position will be moved to the 0 and real also getting incremented to 0. From -1 to both are getting incremented. See, next, when you are trying to insert another one element, the front will be maintained as it is. That is, front pointer will point it as 0 and rear pointer will be incremented. Okay, so here B is inserted, so that now the rear gets value 1. 0 plus 1, 1. Similarly, when I am trying to insert C, again rear gets value 2. When we try to insert C, the rear gets value 2. Okay. So next, I am trying to delete an element. So obviously, I can delete an element at the front of the queue only. So which the element will be deleted? Element which is at the first in the queue will be deleted. So I am deleting, what's that, a. So while I am deleting, please make note of it, while we delete an element, the front pointer value gets incremented. While we are inserting the element, the rear pointer value gets incremented. Okay, so now you are able to understand the difference. Initially front pointer points the 0th position, while I am deleting the first element, there is nothing. So obviously the pointer will move to the next position where it consists of elements, so that front gets 1 here. Okay, similarly, while I am deleting B, again the front move to the next position where the elements are there. It will leave the empty position, so that it will point to the element where it has. Okay, so that now front gets 2. Okay, so likewise, insertion and deletion involves the movement or the movement of front pointer as well as the rear pointer. Then finally, when I am deleting the C, the completely front also, both the queue is completely the queue is empty. So both the front and rear pointer points the -1. Okay, so entry point is called rear and exit point is called as front. Okay, so this is very very important concept in terms of queue. Okay, so please observe the code. First of all, if you want to enqueue any element, what do you mean by enqueue operation? Inserting element, right? Inserting element into the queue. So before inserting any element like stack, we are in need of checking whether the queue is full or not. Okay, when the queue will be when you can identify the queue is full, so if the rear is equal to, if the rear pointer value points the value which is equal to the length of -1, that means maximum size what you have given already, and less than that, one less than that. Okay, so if the rear is equal to capacity -1, then obviously you can understand the stack is full. Otherwise, you are able to insert an element. Okay, so while inserting an element, then what, obviously the front value will be, sorry, the rear value will be, what's that, incremented. So rear equal to rear plus 1 equal to 1 means rear equal to rear plus 1. Obviously, while inserting the element, the front will always in the position of 0. Okay, so you are incrementing the rear and then you are positioning the value in that, placing the value in that particular position. Okay, so this is what the enqueue function. So enqueue, in the sense, what enqueue means, adding an element into the queue. So you are all able to add the element once the queue is if you once you confirmed that the queue is not full. How you can confirm the queue is not full? So if the rear is not equal to, if the rear is not equal to the capacity, maximum capacity, then it is, you can identify it is a what's that, it is able to accommodate some elements, then you can do the NQ function. Similarly, DQ operation, that means deleting. So obviously we know that we cannot delete anything from the empty queue, so we are supposed to check whether the queue is empty. So how we can check it? If the queue is empty, the pointer value will be of -1 only. So if the function returns true, then it is empty. The function of friend equal to 1 returns false, it is of consists of some elements. So we are confirming here that whether the queue is empty or not. So if it is not empty, then we are able to delete the element from the queue. So while we are deleting the element, what will happen? It will, the position of the front position will be incremented. Similarly, the rear value will be decremented. Okay, so that is what the case here. Front equal to front plus plus, that means front pointer will be moved to the next element from the empty space. Similarly, the rear pointer will be in its position, but the thing is, while you are keep on deleting until it reaches while it reaches an empty queue, then both will point to the -1. That is what denoted here. If rear equal to front and rear both are equal, that means both are pointing the same position, then obviously it would be -1. Okay, that means the queue gets empty. Okay, we have deleted all the elements. So DQ function for deleting an element from the queue. NQ for operation, it is for adding an element into the queue. So before DQ, you are all supposed to check whether the queue is empty. Before NQ, we are supposed to check whether the queue is full or not. Okay, so this is the case. Okay, so what we have studied so far is the linear queue. Okay, so in a linear manner we are approaching here. So here we have a drawback. You please look into this diagram. So initially queue is full, 21 to 93 we have stored, but while after some after some DQ process, 21 and 33 gone. So now the rest of the elements are 4, 12, 67, 78 and 93. Suppose if I am willing to add one more element in this queue, even though there is some free spaces in the front's end, so it is not possible to add elements in the queue since it is a linear queue. Okay, so that is what the point here. In a linear queue, once the queue is completely full, it is not possible to insert more elements. So once it is full, it is not possible to insert further elements. And also, if some of the elements were dequeued from the queue, even then there is spaces available, we cannot include the new elements until the queue is reset. Okay, so these are the some of the drawbacks. Okay, so how you can address this drawback in the linear queue? So that is what the idea of circular queue. Okay, with the help of circular queue, we are all able to address the problem in the linear queue of wastage of memory. Okay, so we are all able to add the element in a flexible way. So this is a structure of the circular queue. So in this structure, we are all able to see that the structure itself in a circular format, we are all able to increase the position or increase the pointer position of the rear pointer based on the availability of the elements. Okay, so here this structure is called as the ring buffer. Okay, so see here in this example, so front pointing the position 0, here it is 10, the element is 10. Similarly, rear pointing the position as 4. Okay, so suppose if I want to add one more element in this front, I am able to add it here. Or I will show it. So here now, please wait. So we can add it in the position as. Look into this picture, you are all able to see that how we are able to add an element here. So initially the front point the position as 0, then it is keep on, the rear comes to this last position where the element has. Okay, so I have added, that means here 7 NQs are here. So next, after 5 DQs, from this 7 element, I am deleting 5 elements. So remaining 2 and 4 is here. So while I am deleting, the keep on the front pointer position value will be keep on incrementing, and it leaves all the empty spaces. It will not point any empty spaces. It will come to the element which is on the front of the queue. Okay, so So now the front is here and rear is at the last as the last element. Then next, after 8 more NQs, once again I want to add further more elements, means I'm supposed to include these elements. So after 4, I'm able to increase the rear pointer, and that obviously include the elements up to the further positions. Okay, I hope you are all clear about this picture. So from after this 4, I am able to add 8 more elements: 12, 13, 17, 10, 6, 15, 21, and 54. So according to the number of elements what I am adding, the rear was keep on incremented, and then it is given as the, what's that, yes, the last position of the queue. So this is a circular form of representation which is more comfortable and also more flexible in terms of adding, and that means NQ as well as the DQ process of your queue. Okay, so this is an idea behind the circular implementation. So the algorithm also given here, you can go through this algorithm. So here also we need to check whether the queue is full or not. Okay, if here only thing is, if the queue is full, then it is, we are not able to add it in an effective manner. So that here we need to check what if there is some space only, we are able to add the element, because we here also we are acting with the, or we are creating the queue with some sort of limitations. Okay, so that is what the case of NQ process. Similarly, DQ, we are supposed to check whether the stack is, sorry, whether the queue is empty or not. If it is empty, the same operation and all the same here, same as like our linear queue. The concept here is we are able to include the elements additionally, even though there is some sort of limitations in terms of our circular queue. Okay, so these are the NQ as well as the DQ operation. Both the operations involves the same condition what you have studied in our linear queue, whether the queue is full or not, whether the queue is empty or not. These are the primary function we are supposed to invoke before the major process. Okay, I hope all of you might understand about this NQ, DQ in terms of linear queue as well as the circular queue. Okay. Any doubt in this? I hope we can wind up the session. Any doubt in this? Okay. Thank you all. Thank you so much. 1 minute. I will take attendance.